Now we're recording. We didn't record the first part. Whoops. Yes, so you want me to send the files to you? Okay. Give me 1 sec. Let me stop my share then. And all right. So I need. Yeah. I need to send you. That's RStudio. No Zoom link. So can someone invite this gentleman? He's saying he doesn't have the Zoom, and I will forward you this file so that you have all the files. Actually, can someone else who has their email open just forward it? Oh, you won't have your email. Never mind. Hold on. So everyone just download the file, please, and put it in the downloads folder and open it up in RStudio. All right. What's your email, Alex? A Brummer. Cool. Awesome. So now let's get back to RStudio. Is there anything else? We are recording. We are on Zoom. We're sharing our screen. Shouldn't be any other problems. Okay. In RStudio, it looks like this. This is the code. We're going to walk through it. Sure. Yeah, that's right. All right, so by a show of hands, who is at this point? They have the zip file downloaded, uncompressed. They have unpaired permutation test.rmd loaded in RStudio. Who does not have it? Who does not have this ready and needs help? What are you stuck with? Got it. So you go to the unzipped folder and you open day 1 right here, and it'll have the unpaired permutation test.rmd. Double tap that, and that will open it up. And for everyone who doesn't get RStudio, at any point in the presentation, if you don't get RStudio to work, I rendered out all the HTML files right here. So if you just open it up, it'll show everything that we did. You just can't play with it yourself, but you have all the stuff to follow along on your own. All right, let's proceed. So, okay, so yes, I know the basics of how to code. Raise your hand. No, I don't code at all. Raise your hand. Okay, great. So the basics are each line, you just tell the computer to do something. And just so everyone knows, these little like tilde things are part of RStudio. They're not part of the language. They're just like formatting. They make it look pretty when we render stuff out. So these little things in green, these are comments. It doesn't execute anything. And these things in red, in black here are the actual like instructions. So right here, what I'm doing is I'm reading in the CSV file. So what you'll have to do, everyone, is change this. You'll have to, if you're on a Mac, you just change your username. Everything else should be the same. And all it's saying is telling R, where's the file to read it? Well, for me, it's in users, Don Vaughn, downloads, intro to modern stats, UCLA USC salaries.csv, and that's the file. And then it'll just simply load it in. So if I were to paste that in my console, boop, there it is. It loads it up, and now I have this salaries variable right here that looks like this. You can look at it. Here's the UCLA salaries in thousands and the USC salaries in thousands. Yeah. We'll get there. I don't think we have anything yet, but usually I just bump into it. I try to remove as many as possible. And if not, we have Alex who wrote R, so that's how it works. Okay. All right, I'm gonna keep going. If you are stuck, please have your hand up and Alex will come help you. So, okay, so we load the salaries in. We're gonna talk through it before we do it. Then we're just reshaping the data. We're just changing how it looks. Don't worry about it. I just want to get it into a nice form. And what we're gonna do is we're gonna take these data, you can look at it right here, and all I'm gonna do is I'm gonna take UCLA and USC salaries, and I'm just gonna basically put them on top of each other and then just shuffle them all. And that should shuffle my data. I'm just gonna randomly shuffle all the rows. So we'll walk through that, and then, yeah, let's actually just walk through line by line. Okay, so you knit this. So you can hit knit up here. We don't hit run, we hit knit, and knit turns it into this nice HTML file right here that you can look at. So if you can call print. If I print my salaries, they look like this after I've reformatted them. Here's the school. Here's the salary. So one of the, what would you call it? I would call it an instance. One of the observations that I have is that somebody at UCLA makes $49,000. Somebody else at UCLA makes 51. And if you scroll down, you'll see that somebody at USC makes 24,000 and 74,000. So I'm just looking at my raw data. The most important thing, rule 0 is always look at your raw data. Make sure there's not something funny going on before you start applying stats. Okay, so this person at USC makes $173,000 a year. This person makes 174, 137. So this is what my data look like. So now, as we go through this, I might ask, okay, what is the test statistic on the actual data? So here's what that looks like. I'm gonna take my salaries data, and if you, in R, if you do the money sign, it's just referencing a column. So here I might reference school and salary. So I say, look, on my salaries data, I want you to look at the salary variable and take all of the rows that correspond to USC. So that'll give me all the 70 rows that correspond to USC, and this will give me all the 70 rows that correspond to UCLA, and then I just take the mean of all those values, and then that's what I actually observed, and that difference is $16,358. Actually, what I want to do now is I'm actually going to walk us through it line by line. So you won't have to do this, but I'm going to copy and paste some of this into the console. So the console right here is what actually executes the code. And up here, so they're printing the salaries. Okay, great. So here's my salaries. My UCLA salaries are these. So when I select these data, I'm going to get 70 points. You have to learn how to manipulate your data. You can't do tests. So just simply, okay, those are the 70 observations I have from USC. Those are the salaries. And here are the 70 that I have from UCLA. Those are my salaries. So I want to know from these 70 samples in each group, this is the test now. Here's your data. I know those are different from each other by 16,000, but is that a real difference? So now I'm going to figure that out. So what you do is, you have to, in coding, it's just good practice when you are gonna have a variable, you wanna what's called pre-allocate it, which is create enough space in memory to hold all the things you're about to do. So this test statistic distribution is just gonna hold, I'm gonna run 10,000 simulations of what if I just shuffled this data, how big of a difference might I observe by random chance? I'm just gonna create 10,000 buckets so I can hold all those numbers. So this is just cool. Here's a vector of 10,000 data points, and each one of those is going to be, there we go. That's fine. Cool. Yep. So then each time in this loop, what's going to happen is I'm going to take my salary data that I now have, and I'm going to shuffle it. So I call this shuffled salaries. I take it and I'm going to redraw it without replacement, which means you basically, what sample does is it takes a bunch of random points. But if I have 140 data points in the vector, because there's 70 and 70, if I redraw them in whatever order, I'm eventually going to resample them all. So this is shuffling it. And now I have my salaries in my shuffled simulation, and then I'm just going to simply calculate the difference. All right, so let's say, so here's my shuffled salaries. So this is a little bit abstract. Let's just get to it. So let's say I shuffled my salaries, and then I calculate what the difference is by random chance. So the test statistic for this firm. So this time, what I did is I took my salaries, I shuffled them, and then I redrew 70 into each group, because that could have happened due to random chance. And then I calculate the difference, and it was minus 6,000. So let me show you again. So here's my shuffled salaries. I feel like we're missing something. So here's all my 140 salaries. All I'm doing each time is I'm just shuffling them. Because remember, all we're trying to do is create what could have happened due to random chance. So you don't have to guess. You just literally take the data shuffle them all together in a big bucket, and then you draw out 70 to each of your groups, and you calculate what difference you might have observed by random chance. So that's all I'm doing. I'm just shuffling them in the bucket. I'm redrawing them here, and then I'm calculating the difference. So now let's say shuffle them. So that was the first time. We're gonna do it 10,000 times. So I did it once, and I saw a salary difference of 6,000. Now I'm gonna do it again. Put it out for you. And I got 7,000 as the difference. And now I do it again. We'll just keep shuffling it. And this time I got a difference of 5,000. And then I'm gonna do it again. And I got a difference of 3,000. Then I got a difference of 5, then 4,000, 4,000, minus 4,000, minus 5,000. So your computer is doing this over and over again. It's taking all your data, it's shuffling them all together, and then it's redrawing the groups and looking at the difference in your test statistic. And what you end up getting, I feel like this is not landing. So we're gonna go to the answer, and then we'll come back to it. Here's what you end up getting. Let's look at this, which is, here's my test statistic. So the test statistic is just the difference in salary between UCLA and USC, because that's what I care about. I know the real value is 16,000. Right, all I do is call mean. Mean in this one, mean in this one. The difference of those is 16,000. So now my question is, well, is that real, or do you see huge differences all the time? So to see if that happens all the time, I'm just taking my data, shuffling them up, redrawing my fictitious salaries for UCLA and USC, and then looking at the difference. Most of the time that difference is 0, right? Because there is no difference. You shuffled everything. There was literally no effect of school on salary because you shuffled all the data. Took all the data, shuffle it up. Most of the time it's 0, but just by random chance. If I were to put a whole bunch of numbers in a bucket and redraw them into 2 groups, sometimes you get a difference in the mean. Totally due to random noise. And so most of the time it's 0. Sometimes you see a salary difference of $10,000. Sometimes you see a salary difference of $20,000. And I know it's by a random chance because you did the shuffling. You took all your data points and you just shuffled them up, and then you pulled out your salaries again. And it's random. It's basically like for each salary, it's like flipping a coin. And each time it either goes to one distribution, it either goes to USC or UCLA. And then you take your next salary that you observe and you flip a coin. So you ignore what actually happened in real life. And you just shuffle it and recreate it. And this is what's happening behind the scenes with the t-test. It basically assumes, oh, there's no difference, but based on the data that I saw, you're gonna have some standard deviation of your data, and then it just fits a normal curve to it. And it tries to assess, well, based on what I think the data should look like, where do your data fall? So what you see here is, here's what could have happened by random chance. These are all your random test statistics, and I'll show it to you one more time. But this, when I showed those plots and just shuffling each time and seeing what could have happened by chance, this is that. So you just built this from the data. And this green line right here is what's the actual true salary difference, which is 16,000. So you can see from the data here that here's what I actually observed. When I just shuffled and mucked up all the data, here's what could have happened. I feel pretty confident my effect is real. And you can actually just, and in the code, you'll see that we actually just add it up. We say the observed effect is 16,000, and the p-value that I observed is 0.01. And all I did for the p-value was literally just sum up all of these little buckets right here. How many times by random chance did I get a value bigger than what I actually saw? So it's going to take maybe 10 minutes to totally sink into your head because it's a crazy concept. You didn't just put a formula. You actually, in this loop, 10,000 times, you shuffled all your data randomly between these 2 groups, and you saw what difference might have happened. It'd be like if you had 70 heads and 70 tails, and then you shuffled them all up and drew them out randomly into 2 groups. Sometimes you get more heads in one group than the other, but you know it's 50-50. You enforce it, it's just totally even data, but you just happen to get noise because that's how your experiments work. You have noise. So the reason this is useful is, let's just say you have a different question. Let's say you want to say, hey, what's the median difference in salary between this group and this group? What test would you use? Let's say you care again about income inequality or the levels of the protein, but you don't really care about the mean value, you care about the median value. How do you test for the median difference between group A and group B? I don't know. T-test works on means, so how do you do it when it's a median? The median's a really useful metric, it just doesn't work in calculus, so it didn't get popular. Yeah?
Do this process, the median every time.
Shit, there's an idea. So now we'll start to dissect the code a little bit more, but I wanted to get the big point, which is you're just taking your data and you're just shuffling it up and seeing what differences you might have observed by chance. So there's no reason we have to call mean, so let's call median. Where's mean? So now where it becomes interesting is when you have other things you want to ask. So every time I'm calculating the mean, now I'm just going to calculate the median. See if there's any other means in here. Here's a mean. So all I'm doing is I'm replacing what I'm calculating. Instead of calculating the mean difference, I'm going to calculate the median difference. Median. All right. So then no different tests. Nothing else changes. All I do is I would rerun my code. Now let's see what I get. Ugh. That is ugly. Super ugly. So someone walk me through, what is this? Does anyone else need help with their code, by the way? Can you raise your hand if you're still not able to process it? Yeah, what are your errors?
I have no idea.
Okay.
I've been lost.
Okay, what's your error?
I'm able to highlight and run the top chunk, but when it gets down to the print salaries or
Did you hit knit? Did you hit knit?
I have.
What does it do?
It generates this thing, but
Okay.
just to run, like as you were doing kind of piecemeal, like here I can run that, no problem. But when I get down here, it doesn't do anything.
Can you just manually copy it and paste it down here? Just copy it. All right. Anyone else? I didn't realize we were having tech issues. What's the problem?
That anything after, I can't run salary.
Yeah.
But are you hitting knit? So knit works.
Because it is working.
Yeah.
Yeah.
Great. So all you have to do is if you want to change something, change it in your code, and then hit knit again. Don't copy and paste. I was just doing that to walk you by line by line. Hit knit. Yes. Any other questions that's hard about hitting knit?
I was just going to make a comment.
Yeah.
I had to edit my script because I was missing the thing.
The what? Oh, the dot, dash, the little.
This thing.
That's, yeah, I don't know. That seems funny. See if you deleted it, because I had unzipped the same file and it works for me.
So you changed the median, the mean to median.
Yes.
And test that. With mine, pulling it looks weird.
It looks like you didn't change it. Did you change it 4 times? Because you didn't change it.
Yeah.
Here.
Knit runs the whole thing. It sort of like plays.
Okay, I don't know. I get this wasn't totally clear. It sounds like so. If you want to play with the code, you can, but don't copy and paste anything console. Just hit knit, and it'll just spit out differently. That's it. So now what we're finding is, okay, here's a totally different statistic, same exact method. Can anyone, if anything, look at the p-value. It's an order of magnitude more significant. Why? Why is the median more significant?
They're skewed, like the
Because if you looked at the underlying data, just another thing I hope you get out of class. It's not necessarily about all the stat stuff. We're just thinking about data. If your data look, this is what skewed data look like. They're not symmetrical. You have a long tail. This is true with income, reaction time, protein concentrations, I think in most cases. When you take the mean, you get some value here. When you take the median, it's always less if it's skewed this way. That's because if you added, for example, Jeff Bezos to the income pool in here, the mean would be really high. the mean would be tens of millions of dollars, but that doesn't really reflect us. The median would be almost unchanged. So the median is a really nice metric when you have skewed data because it doesn't get pulled by outliers. And what you have here is that really you would want a test of the median. The median is a better test here because you have skewed data and the differences get washed out by the mean. So if I show you this, the data look like, yeah, the data look like this. They're skewed. So the idea, what's going on? It's getting a little loud in here. I'm just doing a typing thing. Okay, great. So the right metric here is a median, but you don't use the median because no one ever told you to use a median because you can't use a median because there's no test for the median. That's the problem. And so it's really nice now. Now you can use the median as a statistic. Any questions on why it's more significant? It captures the differences in the data more nicely, right? You have this complicated, you have 70 actual points and you're trying to crunch it down to a single number that reflects something meaningful about the data. The mean isn't always the best answer. You really might care sometimes about what's the interquartile distance between the 25th and 75th percentile. There's just a test for that. And there is a test for the median, but I don't even remember what it's called. Yeah, what's up?
So like this, you are eliminating the extremes.
What's that?
You are eliminating the extremes.
I am what? Imitating them?
Eliminating.
Eliminating. Yes. That's a great way of thinking about it.
In a scientific journal, you should say why you are eliminating the extremes. Because it's not correct scientifically to eliminate the.
I would say you guys should be on the defense, or you should, because what the mean, if anything, is including the extremes. Why should you include them? Why is the metric of central tendencies or data, if the data are symmetric, there's no difference. But if you have asymmetric data, why would you use the mean? And like I said, you can't technically in a test. Yeah.
Technical question.
Yeah.
My p-value is just
How different? 0.0008. Yeah, so that's great. So sometimes this is the point. You do 10,000 simulations. There's slight differences in the value you end up getting because we all shuffled a little bit differently. So let's run another experiment. This is actually boiled in with the next question or baked in. What's up with, remember, what are the white bars? What's that?
the number of times that you go ahead.
Yeah, but, so this is what I actually observed is the median difference. What's here? Yeah, that's the random chance, right? So here's what I saw. Here's my random chance. That's all we're doing. This is easy. This took the hard work. And now you're just measuring, well, how is this way different than my random chances? How come my random chance distribution looks so screwed up?
What do you mean? Just that it doesn't look like that?
Yeah, yeah. Oh, look, it doesn't look normal to me at all. Well, maybe I didn't run, so maybe to your point, maybe I didn't run enough simulations. So what's nice about this is you don't have to do anything complicated. Here's what I'll do. Bam. I'm going to add a 0. Now I'll rerun it. Let's see if that cleans up the distribution. So now it's running 100,000 simulations. It's taking your data and shuffling it 100,000 times and calculating what could have been the median difference by random chance. Because you're enforcing the random chance. Because you shuffle it, you are literally controlling and saying, this is chance. So looks exactly the same. Did you do yours?
Yeah.
So do you get a more similar p-value? Do you get 0.001?
No, I got 0.00107.
Yeah, so we got another decimal place of precision that's now aligned. So why is this still funky looking? How come the other one was so pretty and normal? I'll let you think for that. And if you're having trouble with it, you can always hit the HTML files and it'll open up. What's up?
Find the wheel for some reason.
Closer, yeah.
The mean is continuous.
Yeah, the mean is continuous, right? You take the mean, you add it, you change any value, the mean changes. If you change, there's only so many values the median takes. It either takes the middle value or the average between the middle values. If you then you get even or odd number of samples. So you get these chunks because the data are kind of chunky. So you can understand why Newton and other, well, people doing calculus, statistics, didn't want to work with this. How are you going to do a derivative in an integral of this? It's ugly, super ugly. So that's why I think it's not popular. And really, one of the things I hope people take out of this is use the median more. It's a really great statistic. Okay. Depends, you have to use it in the right case, but it's especially for skewed data. Super great. Captured the difference much better than the mean. But it's not popular for this reason. So you can ask sort of any question you want. You might ask, well, you know, all I care about is the board of directors, is the 1% difference. So, all right, fine. Take the 1% of the data from each case and then shuffle all the data and calculate, you know, line all the things up and calculate just the top 1%. What's that value? That's it. So this comes up a lot with like DNA reads and things. People just want to do slightly different comparisons of fluorescence that isn't obvious on how to do it, or they have pairwise linkages and correlations and things. So that's it. So I feel like we could walk through the nuances of all this a little bit, but maybe I'll just leave that to you to inspect on your own. But I just wanted you to get the general point, which is, I tried to comment here. What is the test statistic of the actual data? Okay, just the median here. And that ends up being 23,000. The mean difference is only 16,000. The median is 23, so it really captures that there's a difference. The test statistic distribution is all I'm doing, and all this stuff is I'm just generating what could have happened by random chance. I run what's called a for loop, which means it just does the same thing over and over again. So for 100,000 times, I'm just shuffling all my salaries and then recalculating and calculating the median. But since I'm shuffling, I know it's just noise. Here's a noise median. I just store them in these buckets. I store them in one of these 100,000 buckets, and you can actually see, I actually want to print that out so that you can see how that works. So here's what that looks like. So we only ran it a couple times. Let's run it one more time. So here's my, let's say this is my pre-allocated array. I haven't done any simulations that say they're all sitting there, they're all empty. And what I do is I take my data, and you don't do this, I'm just copying to show you. I'm just paste, this is literally what's happening in one of my loops. Here. Yeah, this is what I want. Oh, it's too long. It's too many samples. What's that?
Did you write this script or?
Yeah, I wrote all this. So here, so let's say, all right, so let's just say I went through, I shuffled all the salaries once, I calculated the median of my noise, and what it'll do is it'll store one value in here. So let's see if we can store this. Okay, when I print it out, where's my little number? There. So by random chance, I'd get a salary difference of negative $9,000. Even though I took all the data and I shuffled it and randomly assigned it to my two different groups, then I looked at the difference. It wasn't zero. It was $9,000 in one direction. So if you do that over and over and over again, all these buckets will fill up with all the different results of the permutation. And so then it'll look like this. So here's what I'm histogramming. Here's, if I were to run this, here's the first 10 runs. Here's all the median differences I got, even though there was no real difference. Shuffle the data, calculate the median. 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 So by random chance, all these values could have occurred. And that's the big distribution that we saw. All these values could have occurred, and it generally looks like this. These are the values that could have occurred, but this is what actually occurred. It looks significantly different. Then you just calculate it. So if we don't have any more questions on the code, I'm going to get back to the sort of core content. And what's nice about this function, you're welcome to use it. It's plug and play. You can just swap out mean for median or standard deviation. We should talk about that one. But you can construct your own statistics and run them. Yeah. Good question. So what does unpaired mean? Who knows what unpaired data are?
That before and after is not correlated.
Yes.
Pair is like, this was the initial 90 something, and then this is the number.
Mm-hmm. And it could be more than just.
It doesn't matter which was before.
There's no link between the samples in each of my sets. So these are 70 professors from USC and 70 different professors from UCLA. They are unpaired. Had I just followed the same 70 professors and looked who happen to work at both universities, then I have paired data, right? Because they're linked. And you ideally want this in your experiments, and we'll talk about it tomorrow. You want paired data because it might be that people made more because they have more years on staff or something, or more years of faculty, and you can sort of understand that difference a little bit better. You have more information. We'll talk about it tomorrow. Absolutely. We'll do that tomorrow. Okay. So we got that. So we did that. We did this. We basically did this. We took our data. We shuffled it thousands of times. This is so, I don't like that at all. We shuffled it thousands of times and we got these values. And that's how we built up this distribution. And then, sorry, this is like killing my working memory. No? And then we compare it to our actual observed statistic and calculate the p-value. We just literally did this. If you look at the code, we do it line by line. Here's the data. Shuffle it a bunch of times. What do I get by chance? Count how many times that's bigger than this. That's the p-value. You look in there, there's a line that just says sum. I just added up. Permutation test. We did this. We did this. We did the p-values. So actually, no, this is we switched this today. So then I want to get the p-value flat, and I moved that to today. So this is important to get right. So what is the p-value in your own words? We got two ideas from earlier. Now that we've gone over and calculated it, I want one more. So what, in your own words now, what would a p-value be? Somebody different. None of you guys.
The fraction of the time that what you observed would occur by random chance.
Beautiful. Yeah, couldn't have said better. So you got to walk out with that. So I hope that we have lots of cortisol and acetylcholine. It's like, oh shit, I didn't know that.
The fraction of the time what you observed would occur by random chance.
Yep. The fraction of the time that what you observed, your actual data, could have observed by random chance. It's the hard thing we don't want. All the times you might have just, your data might just be total random noise. And if your data are really, really extreme, like your example, you have really, really clearly different values, then that should be a low value. That random chances doesn't really explain what you saw very well. It would have to be very extreme. You have to shuffle the data and like somehow all the high values were in one group and all the really low values were in the other group. So when you look at the difference, it seemed really high. So very unlikely to happen. So that's what we do. So the p-value is that. Said another way, it is the probability of observing the data given no effect. So there's no difference in the, let's say, there's no difference in some hormone that you give people to change their mood. So it's a mood change, mood stabilizing hormone. You give them medication, and you have two different groups. And it turns out that that's not real. That's not really a real working drug. So what's the likelihood you would have seen this data given that there's actually nothing behind it? And I just want to pull it out that here's how we usually confuse it. We usually say it's the probability there's no effect. And I heard that earlier. It's like the probability this drug doesn't work given the data. We're absolutely not saying that. You don't know. Remember we talked about the real truth you never see? The real truth is behind the scenes. Like whether this drug works or not, you don't know. Whether, let me give you a different example. Let's say that playing football, if I look at the data, the people right now are reporting higher rates of chronic traumatic encephalopathy from playing tackle football. Is that real or not? So when I put some study and I measure the two groups and I come up with a p-value, it's not the probability that football causes CTE, given the data that I observed. Because you know what? I just do not know. This is a Bayesian inference, but all the statistics you usually work with are the frequentist ones, t-tests or whatever. And that's just saying, look, if we just assume, since we don't know, but let's just assume that there's no effect, how likely or unlikely would I observe these extreme differences in chronic traumatic encephalopathy? And we just did that. If we shuffle all data, it wouldn't be very common. So the CT is super, super high. So the p-value is low. So that's just saying if there was really no effect, our data are not really consistent with no effect. But I can't tell you the answer. I couldn't tell you which one it is. So whenever you hear somebody say it's the probability that there is no effect, or the probability my theory is true, and they're talking about this kind of stuff, it's not that. They don't know. Just remember what you're doing. You don't know the truth. You're just when we shuffle, we're just saying, let's just say there's no effect. Let me just shuffle this data to break any link between school and salary. And let me just see what would have happened. And then see how likely I would have observed my $16,000 difference given no effect. It was low. The p-value was 0.01.
But you can say that there's no effect. No? Like
You what?
if I'm testing the drug on hundreds of patients,
Yeah.
and I see no improvement, but not that they're going worse. Then
You see that there's no improvement, that they are or are not getting worse.
No, they are not getting worse.
There's no change.
So no change. So then I can say exactly that there is no effect.
You could say
Not
that
I don't know. No, I know there is no effect.
you don't know. Is gravity true? Let's start with something really obvious, since we keep going here. Is gravity? This is true, right? We've observed a lot of differences. Can you be 100% sure? How do you explain that gravity at long distances seems to work in the opposite direction and accelerate matter in increasing rates and not pull it back together? Not totally consistent. So we're never, ever, ever 100% sure. That's just not, you just cannot do it. Only in math, when you make some assumption about something and prove something, there's no proving in science. We like to use the word, because your point's good, which is like, look, we're just talking about it. You measured 1,000 people and there was no change, probably good enough. But there are plenty of times when either the data were biased or you just got unlucky with the data. Sometimes people get unlucky with the data and you got a bunch of crappy samples at first. I could prove it to you. I could take a whole set of data that I could manufacture this data and show that here's two groups of data and one definitely had an effect. And I could show you if you gave me 10,000 times, I could get all the no effect. I could get no effect to show up sometimes. It's just how it works. So the important part of this class, is figuring out when is it clear enough to draw the line and what are the real assumptions behind it. That's why we're here. So if you want to make this kind of inference, you want to do a Bayesian stats, and those are cool, but most journals just don't, sometimes you deal with them. Most of the time it's this. You see a p-value fundamentally is this. There is no p-value here, because this is how it's defined. If I assume there was no effect, how likely are my data to have occurred? And if it's smoking and cancer, there's a pretty clear link between smoking and lung cancer. And so by random chance, the p-value is really low, because the probability I observed that much lung cancer if smoking didn't cause cancer is super low. It's just not consistent with the data. So you have to make an assumption. So fundamentally, we're making an assumption that there's not, or there is something going on. It's also not the chance of making a mistake. It's only the first thing up there. And this is a good slide to just look over later. But I think, if you're going to use the p-value every day in your whole career, it should be pretty flat on. It's the top one. All right. Null hypothesis, no effect. So I feel like it's 3 o'clock. We can either take a break for 5 minutes and come back, and then edit to 3:30 or maybe 3:20. Or we can power through for maybe 15 more minutes or 20 more minutes, and then I'll let you go. Which one would you rather do? Want to take a break? Raise your hand if you want a break. Raise your hand if you want to power through. Is that statistically significant, you think? You know what we should do?
For this group, yes.
Yeah. Yeah. Okay, fair enough. Yeah. Yep. Okay, cool. So we'll keep going. So there's the bootstrap. So what do we, let's just recap. I know that was a lot. The first day is intense. There's a lot. We're letting your subconscious brain work at it. It's gonna pick at it. But the fundamental idea is just don't assume what chance is. Just use computers and just build it by shuffling. Shuffle it, see what could have happened. and then just compare. Bootstrap, and those are tests of significance. That's like, is there something real going on? But it doesn't tell you how big an effect. We never talked about, is it a meaningfully large effect? Because if you take, there's plenty of studies, if you take 1 million data points in one group and 1 million data points in another, and you compare across some metric, it's gonna be not exactly equal. So you're gonna get a p-value that's significant. Like no matter how you slice 1 million people, if you have a huge sample size, are they exactly equal or not? Probably not exactly equal. So usually that's why when you add more and more and more and more and more and more and more samples, you'll get an effect. But the question always then comes, like, question is it meaningful? Is a 0.001% increase in cancer rate over a lifetime really meaningfully different? Or did you just dose the rats with so much sucrose that you pulled something out? Or you had so many samples. So that's the difference between significant, like is it real? Is there actually a difference? With magnitude. Is it of a size that I care about? And those are the two things we always focus on. It pops up throughout life when you explain. Most people, when you talk to someone about something, usually all they care about is it real? Is it true? Yes or no? And then as you get more nuanced, you're like, well, how big is it? And then if you get really more nuanced, you say, well, how big, what's your confidence interval? How sure are you that that's the real magnitude? So it's sort of the 3 levels of like information that we talk about in science. So headline is it true? Then how big? Then are you sure? So we talked about the first one. Is it true? Now you know how to do it. Shuffle everything, see what would happen. How does your data stack up? Now we're on the bootstrap, which is, let's say my test statistic is the mean here, your favorite, and we check, what is the mean salary at UCLA? Let's say I ask you that question. Did anyone happen to calculate it on their data? If you calculate it, I think it's $64,000 is the mean salary. You just take the data, take the mean, 64,000. Now I ask you, are you sure? Like if I was to ask you to report, what's the mean salary at UCLA, or what's the mean incidence of breast cancer among women in Southern California? What would you say is the answer? Let's say it's 1%. Say 1%. How sure are you?
But this is again easy because you know how many breast cancers are in California because you're counting them and you're making statistics. And
Sure. What about all the people that don't report it?
What?
What about all the people that don't report it?
I mean, if you have breast cancer, you go to the doctor and then it's not like you don't report it. And you
Plenty of people die and find out that they have types of cancers in their body. It didn't kill them, but they still had breast cancer.
And they died by
Other causes. Sure, anything else.
This is
We find all the time, people, when MRI scans, people come in, not all the time, but they come in for a normal MRI scan and we find incidental findings. So yeah, we all have things that are going on with us.
But this is 0.01%. Low probably.
No, I don't think so.
I don't think it's that low. Breast cancer.
Oh, sure, it's probably higher.
Breast cancer is very common.
Okay, so it'll be the last time we say it. I love that you like the examples, but the point of the examples is to illustrate the larger point. Can you get down with that? Because now it's starting to interrupt what I want to say. So all the examples are, let's say, what's the incidence of Parkinson's disease? Some people get diagnosed, some people don't. Or what's the effect of a particular gene splicing variant on some phenotype? So something that we don't have all the data easily countable. So whenever I say something, just analogize it to that. So let's say we have that. And the question is, when you come up with some number out of your study, let's say you sampled 100 people or 100 mice or whatever, and you come up with some number and you say, oh, well, the mean difference between the control group and the group exposed to some carcinogenic property is 4%. That's the difference in life expectancy. Whatever your metric is, you come up with some number, that's the magnitude. And as an analogy here with UCLA, let's say the mean literally is actually 64. My question is then, are you sure? How do you know it's not 63,000 or 65? So So whenever you come up with a number in your paper, you're not actually, you know, that's your best guess. That's your maximum likelihood estimate usually, but it's your best guess. But it doesn't mean you wouldn't bet 100, you wouldn't bet everything you have that that's the exact number. So there's some amount of uncertainty in it. So really what you end up, you know, analogizing this to what we had before is you have some sampling distribution down here and you draw it. It's being drawn from a population distribution and you're trying to, this is your best guess for the mean, but you don't exactly know what it is. Because maybe it's here, maybe it's here, maybe it's here, maybe you got a sample that got a couple of high samples, maybe it's really here, whatever, but you don't actually know. So there's uncertainty in your estimates of magnitude on how big your effect is. So it's important to tell for, you know, everything should have uncertainty on it because you're never that certain. So that way people can do meta-analyses and they can factor in, let's say I found that this drug causes cancer 3% of the time and I had 10 subjects. And let's say another study found that that drug causes cancer 3% of the time, but had 100,000 subjects. Which study do you believe more? All other things equal, the big one with the big numbers and the confidence intervals on that should reflect that it's 3% and it maybe it's 2.9 or 3.1%, but it's very close. And so that's what we're trying to do. We're trying to say, well, how sure are you? Is there a lot of noise in it? So what you want is you want your observed value and you also want it with confidence values. So how confident are you? And in order to do that, to quantify that uncertainty that our best guess is here, but our data show it might be somewhere between here and here, that is quantifying our uncertainty. So how do we do that? How do we do that normally right now? What's a really simple way? You guys report confidence intervals on your magnitude? So what would you do? How do you do that?
1.96.
Perfect, yeah. Right, like 1.96 times the standard deviation over the square root of n, something like that, if it's SEM. Yeah, because that's like 2 standard deviations. So basically, you just assume that the uncertainty is normal. It's normally distributed, and then you calculate the standard deviation, and it has a nice attachment to probability values, and you basically are putting your 95% confidence interval on. That's what you're doing behind the scenes, and you're just assuming that if this is like probability of how likely my guesses are, it looks like this behind the scenes. Here's my best guess, but it could be this one, and if I were to pick a cutoff that encapsulated 95% of my certainty, it would be these 2 numbers. That's what's going on. Take your data, assume it's normal, which in the case of mean it would be, and then you pick some hard numbers that takes 95% of your data. That's how it goes. Same thing happens with me, you know, when you have any other statistic, though, it's not as easy. Medians are contrived, but even correlation coefficients, you can return confidence intervals on them. And more I'm asking for that. I'm like, well, it's a good way to detect outliers. People have these these single data points that you're worried are like pulling their distributions. It's because they just report the correlation coefficient. It should be plus or minus some confidence value. And with this technique, it's a very easy way to put that on there. So any number you report, the bootstrap, which we're going to get into right now, will teach you how uncertain to be about it and how to put confidence intervals on there. So here's the idea. So today's sort of idea day. Yeah.
So confidence intervals, that's the same as percent error? Or similar?
Confidence intervals would be the right word. Did I say something else?
No, I'm not sure.
Oh, well, percent error could sort of be a lot of things, like you shot an arrow, like how close was it to target? There's an error. So percent error is here. They're different. Confidence interval is given the data. Here's my best guess, but I'm pretty sure it's between here and here. That's confidence interval. But you don't know the truth, right? Remember, you never know the truth. And percent error is like, well, here's my best guess. You know what the truth is, and you can figure out how far off you are. So like for me, maybe I would take a set of data. We just did this project with, let's say, people who are diagnosed with anorexia nervosa and neurotypical controls, and we build a classifier based on their brain patterns to predict. Well, based on their brain patterns, they either look like this or this. You do however well you do, and you compare, you say, what was my percent? What was my error? My error rate was, well, I got it 76% of the time we could do it, but 24% of the time there was an error. That's different than a confidence interval. Confidence interval might be in individuals with anorexia nervosa, the average activation in their visual cortex to particular images was 12% higher than average, plus or minus 2%. That's the confidence interval. It's just that's my best guess. I didn't measure everyone. I don't know if it's true outside of my sample. It's just my best guess. What's that? Super important. Very, very, very important. Because it's really like, if you want to be a good scientist, you have to let other people know how much to trust your studies. Or not. You can say you go screw yourself. I tell journals to reject people that don't put, again, I just am a butthead, but I just feel like you should do the hard work of learning this, and then it's easy. Just do it. It takes you 5 minutes. Yeah.
And the better report confidence interval is that standard deviation.
Yes. Because as we'll talk about, standard deviation assumes that your the best estimates are normally distributed, right? We're back to this whole point. And so with the mean, the law of large numbers says that is true. That if you take the mean of sample, it is normally distributed. But for anything else, you don't know. For like ratios. So we'll do it. We'll do it with the salary ratio between, I think it's tomorrow. We do the ratio of salaries between universities, just like you might have a ratio in fluorescence or a ratio in whatever. And you can find that the error confidence intervals are not symmetric because it's a ratio. It sort of behaves funny. Standard deviation is a proxy to get there. But who cares? What do you care what the standard deviation is of your data? You don't really care, right? That's a proxy for what you actually care about. What you actually care about is conveying to the reader how certain are you. No one gives a shit about your standard deviation of your data. Sorry. Or my data, or anybody's data. It's just this, we just got used to like using it because it's easy. Yeah.
Also, that would be like if our data is normal, like we can the standard or standard error constructed.
Totally. If you're just calculating the mean.
But if it's not like only distributed, we have to use that.
Which, yeah, exactly right. Which, like, yeah, if you look, zoom in at most data are not sufficiently normally distributed. Even height data, they have all this height and weight data. If you sample 1,000 people, it doesn't pass normality. You wouldn't have anyone in the NBA.
So if like the data itself is like normally distributed, like which one's better? Like the bootstrap?
They'll asymptote to the same point. Good question. If you called t-test on my data were normal, it would give you the exact same answer as a fermentation test. Same. Yeah, great question. So that's why I always say this test is as good as all the other ones, if not better. In all, it's Pareto better. Never worse than. Same power. Maybe a little bit more work to learn. Super easy to say t-test. It even calculates degrees of freedom for you. Nice. Yeah. Okay. How are we doing for time? All right, so we have 5 more minutes. So pull your brains back. We're going to do this. We have 5 more minutes. We can learn this, and then you'll percolate on it all night, and you'll dream about statistics. Maybe. Any questions? Awesome. Great. So here's the idea, and it's such a cool idea, I think, which is, here's the problem. What if I told you, like, how are you going to figure out how uncertain you are about a metric? What if I gave you this example? Wouldn't you ideally like to take, like, if this is the true data you care about, you want to observe, let's say the distribution of cancer rates or something, and you're trying to sample it and figure it out, profile it, or what you'd love to do would just be to run the same experiment 10,000 times. Wouldn't it be nice if you just get the data from the NIH and like, okay, I can't ask everybody, and I can do these little small studies around the US, and I can just rerun my experiment a whole bunch of times, and then I'd have a pretty good idea of how uncertain I should be in whatever my measurement is. Because I'll get 10,000 different values for it. Let's make it more concrete. I care about the brain atrophy in people with dementia. That's what I care about. How much brain atrophy is there? Well, I'd love to sample everybody and get the truth data, but I can't afford it because MRI is expensive. So let's say we get a whole bunch of studies centers together, and we scan 10 people all over the US, and basically have a whole bunch of different versions of the experiment. And the thing is, the scanners are different, so they have different values. But on average, I'd be like, okay, well, almost everybody gave me a 10% neurodegeneration rate. So there's 10% of the brain matter was missing. Some people had 8, some people had 12, but overall it was 10. If you looked at them all, you'd be able to say, okay, well, 10% is our best guess, and it's between 8 and 11, just based on the data. It'd be really simple to put confidence intervals on that. But often we can't do that. So here's the idea behind a bootstrap. There's really only two things to learn. There's the permutation test and the bootstrap. So this is number 2. Big idea is it's too expensive to do that. So what if instead we replace that? We assume that the data we got, our 70 samples of our salary data, was a pretty good proxy for what the real population data looked like. So you did a pretty good job. That on average, if I looked at the data, the real data and my sample pretty much have the same shape. Then what you could do is you could take your real data and basically we'll tell you how to do it, but you rerun your experiment many times. And each time you'll get a slightly different set of data from here. And then you compute, let's say, the mean each time, and you'll get from that a whole variety of very slightly different means. And what you'll end up getting, we'll skip through all that. What it looks like is you'll have, if I reran my experiment 10,000 times, I'd have 10,000 slightly different means based on my data. If I could rerun my experiment. And then I would say, oh, well, my best guess is here, and my confidence interval, since I ran it 10,000 times, I can just find, I know exactly how sure I should be. Out of my 10,000, 95% of them are between this number and this number, because I can literally just look at it. I have 10,000 values here. I just line them up in order and say, what's my 5th and 95th percent number? And that's my confidence interval, and that's what you return. Here's the idea behind it, and then we'll go, and I'll let you just churn on it. So you use your data to rerun your experiment, and you might say, well, how the hell do you rerun an experiment with the same data? It doesn't make any sense. Let's just assume that all the observations that you got were independent and equally likely. So if you got these salary, this is your actual sample data. You actually drew these, let's say these 6 samples. To rerun your experiment, you would assume all of them are equally likely and just randomly, it's like a die, and you roll that dice 6 times and record the numbers. So let's say you got 40, 42, you happen to get 42 twice, you happen to get 90 twice, and you got 50, you didn't get 55 or 65. So you're basically assuming like, yeah, this is a pretty good sense of what my population data look like. So if I run my experiment, it might have turned out this way. It could have turned out a slightly different way. The data could have happened this way. So you're basically factoring in the noise that could have happened from sampling. You're rerunning your experiment enough times, you get a slightly different mean value each time. So let's say the mean on this one's 59.8, okay? That sounds good. And if you do that over and over again, you'll get just very slightly different means. So instead of doing the normal method of mean plus or minus your standard deviation, and just assuming it looks like this, same thing is with the permutation test. You just do it. You just take your data and you build it a whole bunch of times and you get this distribution. And then you can infer the confidence interval. And for the mean, it'll be the same number as the standard deviation. But if you care about any other metric, or you care about having, if you have any other metric, then this is your way to do it. So we can do it for the median, and we can find what's, my median is this, and it's probably between here and here. You take your data, shuffle it, and resample it. We call this resampling. You rerun your experiment, you get a different median. Do it again, you get a different median. You just do that 10,000 times, just like the permutation test. So what that looks like is this. We talked about before. You take your data, you shuffle it, each time you get a slightly different answer. And then at the bottom, you have a pretty good idea. You're like, okay, well, this is certainly my best guess for the mean salary, but it could be between here and here if I want to be 95% sure. So you have all your values. So, and just so you know, this is how that might work in traditional statistics. You have your data, you fit a normal curve to it, in this case, and then you have a distribution about it. Mean plus or minus the median minus standard deviations. That's what you get. So essentially what we're doing is, this is our best guess. So our best guess would be the mean salary is $64,000 and it's between 57 and 69. That's what you'd report in your statistics. You have your best guess and your confidence intervals. And that's what that's trying to reflect here, is that these data allow us to say, well, that's my best guess. But I have to have some amount of uncertainty because you're never totally sure. So it becomes, tomorrow we'll go over it, but we will get into the correlation. It's a great way to do it. You could say my correlation is 0.3, but it's certainly between 0.25 and 0.7, or whatever data end up showing. So you'll have a really clear way to put, to tell the reader and tell anyone else that you know how certain or uncertain you are. So now I want to just recap what we talked about today. So the population distribution is what you actually care about. That's your effect. That's the truth. That's why you're collecting the sample data, to make an inference about the population distribution. Your test statistic is what you're calculating: mean, median, standard deviation, fluorescence ratio, and anything that you care about, interquartile range. Bootstrap, we just talked about that. That's the ability to rerun your experiment a lot, and you do to characterize variance. So I might take my correlation data, as we'll do tomorrow, and you have a correlation, and then I'll just bootstrap it 10,000 times, and you get slightly different correlations each time, and you can diagnose outliers, and you can tell the reader, well, here's how uncertain I am. And we talked about this. Permutation test is to shuffle group membership a lot. So that's the shuffling thing. You just simulate random chance, and then you build your distribution. And that way you can test other things besides the mean. And tomorrow we will get into the bootstrap example. Thanks.
I have a question real quick
Yeah, what's up?
about Bootstrap. Are you familiar with using Bootstrap to simulate propagation of errors?
No.
Cool.
Yeah, no, I couldn't tell you.